Alright, so this brings us to lecture 5. So I can get another light on here. So lecture 5 is on interior closure and neighborhoods. And so the interesting thing I think about all of this is, of course, we've seen definitions of interior and closure and neighborhood before in Euclidean context, where all of this is based on distances and the metric with respect to the reals, right? But in this section, we're going to define all these things just in terms of set theory, basically, and the topology. So it's kind of neat in that sense. So first thing, if we have a subset of a topological space, then the closure of B is denoted B bar, and you can say it's the intersection of all closed sets which contain B. All right, and the points in the closure of B are said to be adherent to B. All right, so like example 1, if A is a subset of B, and if B is a subset of C, then we also have A as a subset of C, right? So the closure of A is a subset of the closure of B. And likewise for a family, if we have a family of subsets of X, then the union of the closures are a subset of the closure of the union. Why? Well, because the jth one is a subset of the union for like arbitrary j, right? Which means that because of this property right here, then the closure of the jth one is a subset of the closure of the union. But that implies that the union of the closures is a subset of the closure of the union. So that's kind of neat. Another definition which is important to know about, because this actually gets used in places where you actually apply topology. There are often interesting sets with a particular property which are dense in the space, even though the entire space is not having that property. And as such, you can sometimes use an argument based on density to extend something which is true just on part of the space to the whole space, basically using sort of a limiting process. Anyway, so here it is, definition. I think I can zoom in a little bit more. I don't know why I'm only writing on. Zoom in just a bit more. I'll probably forget I zoomed in, and then it'll be a problem later, but hopefully I won't. Subset is said to be dense if the closure of the set is the whole space. Equivalently, A meets every non-empty open set of X. So if you if you have an open set in the topology, and you look at a dense set, if you intersect that open set, as long as it's not the empty set, there's got to be at least one point in the intersection. That's what it means to meet a set, okay? To meet means the non-empty intersection. So generally, likewise, if we have A as a subset of B, then to say A is dense in B means that the closure of A contains B. All right. So here's some examples. Get it up here. Come on, there we go. If the topology just is the silly topology, then and if we have a non-empty set, then then the closure of A is just X again. So yeah, because what are the closed sets in this? The closed sets in this are just the whole space or the empty set. And so what are the closed sets which contain a non-empty set? Well, the whole space. That's the only closed set that contains the set space A. So the closure is then by definition the whole space. On the other hand, in the discrete topology, every set is open, which means the complement of every set is is also open, and as such that means every set is both open and closed in the discrete topology, and that implies that the set itself is closed, which means if you take the intersection of all sets which contain A, that intersection will just go down to A itself, because A is itself closed. All right. If you have the rational numbers with the Euclidean topology, then the closure of the rational numbers is the real numbers. The rational numbers are dense in the real numbers. You probably explored that in some depth in your real analysis course, actually. And in the cofinite topology, any infinite subset is dense. Remember, cofinite means C is closed if and only if C is the whole space or C is a finite set. So if you think about an infinite subset, right? If you have a closed set which contains that infinite subset, then it must be that that closed set is infinite, right? Because you can't have a finite set contain an infinite set, right? So that means C is not finite, and therefore that the closed set which contains J must in fact be the whole space. Therefore, the closure of J is X itself, and J is dense. So the cofinite topology, it stretches your brain a little bit, but it's a good elementary topology that we can sort of test our ability to stretch our mind around definitions. It's a good learning ground for that, a good testing ground for our intuition, or to break our intuition, perhaps, at times. Let's see here. So here, next up we have the interior. So the interior of a subset of X is denoted B upper, let's say B degree, I don't know, B upper 0. It is the union of all sets, union of all open sets which are contained in B, all right? Which means that the interior of B is the largest open set contained in B. And by the way, points in the interior are called interior points of B. All right, great. So notice that the definitions of closure and interior used only set theory. There was no reliance on distance, and no reliance on distance was needed for this abstract topological setting, which is, yeah, cool. Little theorem: if B is a subset of X, scooch it up here a bit. If B is a subset of X, then B is open only if B is equal to its interior, and B is closed only if B is equal to its closure. And moreover, if we take the complement of X by the interior, we get the closure of the complement. So you can check on that theorem there. Let's see here. These are probably like nice, relatively low-level test questions. I don't think these would be very hard to prove. So I'll let you look at that. Now, here's some just simple examples in the Euclidean topology. The closure of any of these finite intervals is the closed interval, A to B. The interior of any of these finite intervals is the open interval from A to B. So it works just kind of like you'd expect in the usual Euclidean context. All right. And again, I should mention, when we hit the lecture on metric topology, I think that's where we'll recover some of the more traditional views we have of these words, open and closed and so forth. But, that's lecture, what are we on? Lecture 5, so 6. Lecture 7, I think, is the metric one, most likely. Anyway, here we go. The boundary, denoted partial B, it's the closure with the interior removed, all right? That is logically equivalent to the closure intersect the complement of the, excuse me, it's not the complement. I forget my bars are not complements sometimes. All right, so the boundary is the closure of B with the interior removed, or you could say it is the closure of the set intersected with the closure of the exterior of the set. In other words, the boundary are the points which are in the closure of both the set and its complement. which is really just a fancy way of saying that they're right in between being in and out of the set, right? Like, when I teach calculus, I might teach a boundary point as a point where if you're on the number line and you're like standing over it, you'd have 1 foot in and 1 foot out, you know, something like that. All right, anyway, the boundary of B contains points which are adherent both to B and to x minus B, to its complement, all right? So here's some examples of boundaries from a somewhat familiar context. The boundary of all of these finite intervals is just the 2-point set containing the endpoints. There is no boundary in the whole real numbers, right? The boundary of minus infinity to infinity is just the empty set. The boundary of a to infinity would just be a. The boundary of minus infinity to b would just be b. Now here, this is all, again, within the Euclidean topology for R. If you were working with the reals extended, you know, if you extended the reals with a copy of infinity or perhaps infinity and minus infinity, then we might say something different, all right? But then you'd also be obligated to define the topology on such things, and I suppose we could do that, but not today. All right, so next up we have, this is page 3 if you're keeping score. Next up here we have the definition of neighborhood. So x is a point, and this is a little bit slippery, so pay close attention here, but if x is a point in a topological space and U, a subset of x, is said to be a neighborhood of x, if there exists an open set V such that V is contained in U, in other words, U is a neighborhood of x if it's an interior point of U. See, to say it's an interior point is to say that you can find an open set around that point. If you go back and look at the definition of interior point, you'll see that's not an unreasonable statement. Although that might, technically, that really shouldn't, in some sense, be a, maybe even like a little lemma, right? If you have a set, and, I mean, there's not much to it, because the interior was the union of all, it was the union of all open sets contained inside the set. So like the interior of U, it's the union of all open sets contained in U. So of course if x is a point of V, then that means it's contained in the interior of U, and that means that x is a quote-unquote interior point, according to that definition we made a couple minutes ago. But anyway, neighborhood, a neighborhood doesn't have to be open. See that? Like this definition allows U to be any old set. It doesn't have to be an open set. I mean, it could be an open set, but it doesn't have to be, all right? So here's an example. Minus 1 to 1 is a neighborhood of 0. Why? Well, here's my proof. Because minus 1 to 1 is a subset of minus 2 to 2, and that is a open set. I'll tell you I don't have it backwards. Just a second here. Watch me mess it up. I need V as a subset of U. Oh, rats. I've gotten the order of things messed up here. Yowzers. Come on. All right. So minus 1 to 1 is a neighborhood of 0, since so this is not not the way. This is not the way, okay? So what I should say something like is, you know, minus 0.5 to 0.5 is a subset of minus 1 to 1. So I'm thinking of this as being the quote-unquote V, the open set, right? And here's the U in this, in this definition at play here. And so we have that open set is contained in there, right? And then 0 is an element of minus 0.5 to 5, right? Curses. 0 is an element of minus 0.5 to 0.5. Man, I have no room to write here. So that means, and notice that minus 0.5 to 0.5 is open in the Euclidean topology on R. All right, so anyway, minus 1 to 1 is a neighborhood of 0 because there's an open set inside minus 1 to 1, right? Namely minus 0.5 to 0.5, which has 0 in it. That makes minus 1 to 1 a neighborhood of 0. My choice of minus 0.5 to 5 is by no means unique, right? You could choose all kinds of stuff for that. But sorry about that. I got the inclusion of V and U there flip-flopped. I should probably try to write these notes when I'm more awake. Sorry. Okay. Fortunately, I haven't scanned it yet, so there's that. I was thinking I should scan these at school today. I'm glad that I didn't get to it actually now. Okay, so hopefully tomorrow. Anyway, remark. If we have a family of neighborhoods, we'll call it IX of X. So this means it's a collection of neighborhoods of X, right? Then A subset of X, we have that the interior of A, all right, would be X and A such that A is an element of that family of neighborhoods. A subset is open if and only if it is a neighborhood of each of its points. All right. So let's think through this a little bit. We have a family of neighborhoods, right? And of X. The interior is the union of all open sets which are contained in A, right? So if X is an element of A and there's an open set around it, I mean there has to be an open set around it if it's part of the interior, right? So let's see here. Of course, to say A is an element of A is a neighborhood of X here, right? That means that there exists a smaller set within A, possibly smaller set within A, which is open, containing X, which means that X is an interior point. So yeah, I mean, I think this makes sense. I'm always a little bit suspicious because I've used these words with a different definition in previous courses, and I want to make sure I'm not just bullying myself into thinking I understand something when I haven't quite thought through it. But so don't be afraid to really check yourself on it. All right, anyway, here we go. Theorem lemma 3.20. Family of neighborhoods of a point X is closed under extension, number 1, and under finite intersection, number 2. What does I mean by that? I mean that if we have U is a neighborhood of X and U is contained in V, then V is also a neighborhood of X. All right. All right, and also if U and V are neighborhoods of X, then the intersection of U and V is a neighborhood of X. Okay. So I think this notation I of X it seems like he's using it for not just a family of neighborhoods, but the family of like all neighborhoods of X. So let's see if that's kind of clear in the proof here. All right. I mean, I could imagine a family of neighborhoods where I just fixed it to be a finite collection of them, and then, I'm not sure that makes sense. I'm thinking through it here. All right, so let U be a neighborhood of X, and suppose U is a subset of V. Then, by definition, there exists V naught open in X, with X containing X point in V naught, right? X an element of V naught, and V naught contained in U. All right. But then that means that V naught is also contained in V because it's a superset of U, right? So that means V naught is a subset of V, and therefore it's a neighborhood of X, and therefore it's a neighborhood of X. Consequently, it's contained in I of x, which is, he's using this notation for the set of all neighborhoods of x, okay? Yeah. All right, 2. I'll set aside the question of whether or not it's interesting to ask if we can look at a family of, like, not all neighborhoods, but just like some of them. I know some books, certainly in analysis, there are books which just look at open neighborhoods of a point, you know. But whatever. Number 2, if we have u and v are neighborhoods of x, then there exists open u naught v naught subset of x for which x is an element of u naught, x is an element of v naught, and u naught's contained in u, v naught's contained in v. That means x is in the intersection of u naught and v naught, and of course u naught intersect v naught is an intersection of open sets, which is open by axiom 3 of our definition of topology. And moreover, the intersection of two subsets is a subset of the intersection by set theory, and consequently, that shows you that u intersect v is itself a neighborhood of x because it contains an open set which contains the point x. All right, so yeah, there it is. Now on to the page of 4. What do we got next here? All right, what we got? Lemma. Let B be a subset of a topological space X, a point X, and X belongs to the closure of B if the intersection of U and B is non-empty for every neighborhood U of X. Let's see here. The subset of the topological space X, a point X in X, belongs to the closure of B if if B meets every neighborhood of X. Let me read that again. A point X in X belongs to the closure of B if and only if every neighborhood of X intersects B non-trivially. Well, let's see if I prove that. Maybe. Here we go. Proof. Recall that X is not an element of the closure, all right, if and only if X is an interior point of X minus B. All right. Let's see here. So if X is an element of the closure of B, that's one way to look at it, is that's the intersection of all closed sets containing B, right? So if X is in the closure of B, that means that X is an element of every closed set which contains C. All right. But if X is not an element of the closure of B, that means that there exists C naught, some closed set, which contains B, and that X is not an element of that that closed set, right? So I'm just negating this right there. Okay, hence X is an element of the complement of X by C naught, which is a subset of X minus B. So here's a picture over here of the complement of X by C naught, and here's a picture of the complement of, I knew at some point it would get me. I guess we're at that point now. Here we are. I'll zoom out just a bit. There we go. So here I have B is a subset of C naught. So the complement of B, since B is smaller, its complement's bigger, basically. And since C naught is bigger, possibly bigger, its complement is possibly smaller, because you're, the opposite of C, everything that's not in C naught is in its complement. So that's why it's inclusion reversing, right? So like B, a subset of C naught, means that X minus C naught is a subset of X minus B, right? So I argue what this means is that X is an element excuse me, x is an element of the interior of the complement of x by b, if and only if there exists a neighborhood of x such that that neighborhood is a subset of x minus b, and the lemma follows. I don't know if I have anything more to add here at the moment. Just thinking. All right, I better move on before the children come and get loud again. Here we go. So next up, definition. Let x be in X a subfamily J of the neighborhoods of X is called a local basis of neighborhoods at X if for any U, any neighborhood of X, there exists a element of the subfamily, right, such that that is a subset of the neighborhood. All right, it's a local basis of neighborhoods. So like example 1, if we fix U naught as a neighborhood of X for a given, let me see if I can zoom in a bit again. We don't need all that margin, do we? All right, so if we fix U naught a particular neighborhood of X for a given point X in topological space X, then for all neighborhoods U for which U are contained in U naught, right? So if we look at all the possible if we look at all the local neighborhoods which are subsets of a given local neighborhood, then that will form a subfamily of neighborhoods, which is going to form a local basis. So let's see here. So, okay. Number 2, if B is a basis for a given topological space X, then open sets in B which contain X form a local basis at X. Yeah. So you got to look back at that theorem 3.7 to see why 2 is true. This is the one that gave you the condition. If we have that condition on the basis, then it generates a topology, remember? So that took us some work. But, all right, I'm going to move on here. So I wanted to do an exercise for you guys. And I'm trying to do that in this lecture and the next. I can't always do that, but like sometimes I get stuck. Well, I know I try to find a problem in the book which is not overly technical that's good for one of these lectures, right? And unfortunately, you know, I've already assigned you guys a lot of the problems which are, you know, sort of moderate to easy. All that's kind of left for me, for the most part, are really like the ones with his little coffee mug or something. And I know that I do not have the elasticity in my schedule at the moment to do a coffee mug problem. So, so anyway, but this one's good. This one's, I learned a lot from this problem. This is a good problem. So here it is. This is exercise 310 on page 45 of Manetti. And I like this problem. I think I can think of a lot of ways to change this problem a little bit and still make it an interesting problem. And not just for your class, but like for any future class I teach in topology. I think this, I really like this example. So what we have is we have the plane, R2, all right? And its topology is given by the empty set, the whole plane, and then disks, open disks centered at the origin of radius r. So d sub r, I'm using a notation x comma y such that x squared plus y squared less than r squared, all right? So the first question that the book asks is this a topology for R2? Well, first order of business, is the empty set and the whole set in the topology? Well, yeah, by definition. So that part was easy. Now, what if you had you know, two disks of radius r1 and r2, If you think about it, then if you let R be the max of R1 and 2 and you let little r be the minimum of R1 and R2, you can pretty easily convince yourself that the intersection is whichever one's smaller is the winner in the intersection, right? And whichever one's larger is the winner in the union, right? Because in both cases, one or the other is a subset of the other. So you just think about it for a minute. You can convince yourself that the union or intersection of two of these d sub r's is again a d sub r. Now, in particular, if we had R1 less than or equal to R2, you can specifically easily see that we have disk of R1 as a subset of disk of R2, and that would mean that the union of the R1 and R2 disks would just be dr2, whereas the intersection of R1 and R2 would just be dr1, like in my picture over here. All right. So is it a topology, though? All right. Consider an arbitrary union of d sub r. And we're not going to worry about R2 and the empty set. I'll leave those to you guys, all right? So suppose we're just unioning these d sub r's, all right? So if the union over d sub r are in some index set, well, if I, right, is not bounded above, notice that I here is a subset of positive real numbers, actually, yeah? Because these are labeled by positive real numbers, so we have that. We can view I as a subset if I is the set of all possible indices that we're looking at, then we're looking at a collection of subsets of the reals, all right? And as such, it makes sense to talk about I being bounded above. So if it's not bounded above, then the union over d sub r is just equal to R2, all right? But if I is bounded above, then the union would just be it will be equal to the disk, which is the least upper bound of I, all right? And then again, it's an element of the topology. So yeah, it's a topology. Now, so for example, if you were to take the union over radii from 3 to 10 of d sub r, you'd get d sub 10. Okay, great. And then it asked a question which I thought wasn't interesting for a second, but then I thought to myself, no, that's too simple. And I called up my brother and I said, I want a second opinion on this. And it was talking to him, I realized the stupidity of my ways, but let me explain to you what I did wrong, and then we'll talk about what I did wrong. So what's the closure of I call this the unit hyperbola, or you could call it it's a hyperbola. It's the y equals 1 over x curve in red here. Okay? What's the closure of this in this topology? And so my initial thought was, if I look at little open disks, right, then every open disk has got points both inside and outside, right? So like one way you can look at a set being closed if it contains its boundary, right? If a set contains its boundary, I believe we could say it's closed. And surely this contains its boundary, right? Because every point on the hyperbola is a boundary point, right? Because I can look at these little open disks and they've got points inside and outside. And that's where you have to stop yourself, right? What am I talking about, these little open disks? Ooh, I'm using what's built in my brain, which is the Euclidean topology in the plane, right? But that is not the context of this example. This example, we are only allowed to use open disks centered at the origin for our open sets. So that's not the case. The closure. So I thought the closure was just the curve again. All right. And in the Euclidean topology, the closure of the hyperbola would just be the hyperbola again, because it's a closed set. This curve is a closed set in the Euclidean topology, but it is certainly not in this topology of example 7. So then the question is, if you look at the intersection, right, of all closed sets which contain the hyperbola, well, what's a closed set? A closed set is one whose complement is open. So basically you have to think about rats. I wish I had a colored pencil handy here. I don't think I do. Oh, phooey. Well, I'm gonna make this picture ugly. So think about this. If we go, let me do it. I'll do it over here. I'll do it down here, okay? So if you think about it, if this is the unit disk, right? Closed unit disk, and then you take all the points outside, right? Everything outside. The whole thing outside, right? In other words, like say, you know, x squared plus y squared greater than or equal to, let's say, 1 for the sake of discussion. All right, there's the unit circle right there. Then this set, right? I'm not trying to add to this picture here. I'm trying to draw a separate one. So let me draw a little dividing line there. So this set here, and I'll zoom in stupidly. This set here, right, is closed in this topology because if you take the complement, you just get the open disk of radius 1, which is by definition open. So the closed sets in this topology are exterior, well, I would call them closed exterior annuli in the regular topology, right? They're like, it's like a circle, you know, and the boundary there is actually there. It's not dotted. It's the solid circle, and all the points outside. That's a closed set because the complement of that is an open disk, which is by definition open. So those are the closed sets. The closed sets are the space exterior to circles of various radii. So if we look at the intersection of all closed sets, then it starts to become clear that the intersection of all closed sets which contain the hyperbola, they're given by, you know, like the plane. So basically you're looking at, let me get it in here. You're looking at the closed sets are the plane with the disk removed, all right? And if you just think about that geometrically, it's everything is contained in this as long as the radius has to be, actually it's not greater than or equal, I should say that it's the radius less than, my bad, less than or equal to 2, right? Less than or equal to 2, those are the interesting ones, because if the radius is less than or equal to 2, you're looking at like, so in this picture, if I did that in this picture down here, that would be like the radius 1, you know? So my, that black dotted circle that I have on the bigger picture, it would be out here somewhere. All right? And so like, you need it to be less than the square root of 2 in order for this closed set to contain the hyperbolas, right? But if you think about the intersection of all the ones that contain it, they're all, the intersection is governed basically by the radius of the square root of 2, 1, because that one is the closest you can get to the hyperbola without crossing over that point, these points, and losing part of the hyperbola, thus not containing the hyperbola. So, yeah, so the closure of the hyperbola is actually the plane with the disk of radius the square root of 2 deleted, which to me was both delightful and surprising, and just evidence again that, try as I may, it's really hard for me to free myself of my implicit bias towards the Euclidean topology. Like, it's just, it's ingrained, you know? Anyway, I think that's it for this lecture. Up next, I believe we're looking at continuous maps. So, thanks guys.